minus 2 little r big R sine theta d theta. My 2's cancel out. What I'm left with is sine theta d theta is equal to s ds over negative little r big R. And so we finally have gotten rid of a variable. Got something for this, or something for that now. So plugging that in, this becomes big G mass 1 sigma big R squared 2 pi I hat, just that bit up front, over R big R, the negative up front, and I'm left with negative ds over s squared cosine alpha. We are now down to 2 variables. Now we just have to connect alpha to it. And we're going to do that by law of cosines.
Are we trying to find like a general equation or something?
We're trying to find out what is the force on inside this uniform shell. What is the force of gravity on on some mass inside of it?
Do we have a question like this on a test?
I have not done so far. Is the question, why are we doing this?
Yeah.
You're not expected to derive this, right?
Well, I'm doing it now, so, you know, I will be testing your memorization. And you can see what my memory is, because I keep checking my notes here. I'm doing this because I want you to see how some of the stuff that you have been doing in the past all comes together in a problem like this. The fact that so many of the problems you deal with gravitational pull is you have these 2 masses, you plug and chug into a formula, and I want to show what it looks like if you're not just straight plugging and chugging.
Okay.
That it is bringing in the trig that you've had in the past, it's bringing in the calculus you've had in the past, and so for some of you more present. It just brings in a whole bunch of stuff, to use the technical term. That's why I'm doing it. And so leaving that there. And I'll leave that for now.
I have a question.
Yes, ma'am.
Where did the S go? Like,
That S?
yeah,
Right there.
there.
Oh, thank you. Anything else I leave off? All right. Thank you. So that S is going to cancel out with one of those.
I'm confused why you were able to take a derivative of just that one piece of the function.
Why not? If instead, I'm trying to think of another way of actually doing it.
Usually you're supposed to take the derivative of everything and not just one thing.
I did do the derivative. I took the derivative of this. Those are constants, so that's why they're 0. And I took the derivative of that. I got the d theta and the ds.
I didn't see that step.
Okay. Yeah, it should. You should have at least 2 differentials in an equation. I guess an even number of differentials. Does that answer your question? Okay. All right, now. Same triangle. What's big R squared equal? Do we want to take a shot at it?
Still the green triangle?
Still the same triangle.
Is it S squared? Letters? I don't know what that one would be.
Little r squared.
Yep, little r squared. Yeah.
Wouldn't it be minus little r squared?
No, the law of cosines always starts out with, you got the three different sides here. One of them squared is equal to the sum of the other two squares, and then the minus sign shows up.
And it's R.
Little r. No.
There we go. Now we can solve for cosine alpha. So cosine alpha is equal to big R squared minus S squared minus little r squared over negative 2SR. So what I'm going to do here,
You got a minus there and a minus, one minus too much.
yeah, all right. So now, the only constant I can really pull out here is this 2. I guess the 2r can come out in the denominator. So I get negative g m1 sigma big R squared 2 pi I hat over little r big R. And then putting that in there, I can pull out a negative 2 little r. And I'm left with ds over s times what I'm left over, which is big R squared minus s squared minus little r squared over s. Because I pulled out the negative 2r. Yep. Now, this is just a constant sitting out here. Writing it over and over again is just going to lead to mistakes. And so what I'm going to concentrate on this. So that integral, ds times r squared minus s squared minus little r squared over s squared. We now have it down to a single variable because big R and little r are both constants. So now we can know our limits of integration. What is the smallest value of s and what is the largest value of s? Because remember, s is the distance from our point P to a point on our sphere.
Zero is the smallest.
No, that would only be the case if the point P were on the surface itself. What's the closest that point P is to the surface?
Are you looking for a number?
I'm looking for actually a small little formula. In terms of our unknowns here, what is the closest that point P is to the surface? Where on the surface is it closest?
I believe P plus little r.
You said T?
P plus little
P is just a point in space. Little r is the distance from there to there. Where on the surface here is point P closest to the surface? Say when.
Like a pi.
Here.
There? So what is that distance? In terms of the letters we have on the board.
Is it, big R minus little r?
Yes, it is. Because again, this distance from here to here is little r. I didn't label it there, I labeled it here. What is the biggest, farthest that point P is from the surface?
Big R plus little r?
Like you mean it.
Big R plus little r.
We now have limits of integration. We got a problem we can do. So this becomes the integral from big R minus little r, big R plus r, ds. And I'm going to break this up into, do I really need to break it up? No, yeah, I do. So this is going to be r squared minus little, big R squared minus little r squared over s squared, plus the integral, minus the integral, big R minus r, big R plus r of, well, ds of s squared over s squared, which is 1 ds. And this comes from, I'm left with a negative s squared over s squared. Now let's do the easy one first. What is this integral equal to?
Big R plus R minus big R minus R.
So we're left with s from r minus r to r plus r, which is r plus r minus r minus r, which is 2 little r. So that's this piece right there. The other one. Well, I've had this r squared, big R squared minus little r squared, which is just a constant. So that first piece becomes big R squared minus little r squared times the integral from r minus r to r plus r ds over s squared, or as I prefer to write it, s to the negative 2 ds, which is big R squared minus little r squared, times, well, what's the integral of s to the negative 2? So negative s, negative 1 over s, from r minus r to r plus r, which is big R squared minus little r squared times negative 1 over big R plus r minus negative 1 over big R minus little r. Oh, we're really near the end. This bit right here, well, get a common denominator. So this becomes negative r minus r plus r plus r over r plus r, r minus r, which is two r over r squared minus r squared. When I have this sitting out front, that's going to cancel out with this denominator. And so what I'm left with is this first piece right here, which ends up just being 2r, minus the second piece right there, which is 2r, which is
0.
There are two ways of looking at this. One, wow, it's really cool. We did all that complex stuff and it came out with such a simple answer. Or, We went through all of that just to get 0? You take the pick about which way you want to take it. The students who have expressed an opinion in the past have always been the 0, really?
So what does that mean?
That means that if I have this uniform sphere, that if I have a mass inside of it, it experiences no gravitational pull whatsoever. The point here is not going to be pulled towards the center, not going to be pulled towards the outside. It is attracted from all over the place. So conceptually, if I've got my sphere here and I have a point here, it is much closer to this side, and so it is experiencing a stronger pull over here, except I have fewer particles on this side. Here I have more particles with a weaker force, and it balances out.
So there's like, if there was a hollow planet, there would be no gravity inside of it.
If it were, right, or at least small, it depends upon the distribution of mass. We did start with the assumption that the mass was distributed evenly. But this allows us, going to the planet idea, instead of just a thin shell, suppose we have a thick shell, and you are somewhere inside here. Well, this is just a thick shell, it's just a series of small shells, of thin shells. It's an infinite number of infinitesimally thin shells. And so each of the thin shells exerts no gravitational pull, net gravitational pull, and so it's still no gravity inside here. And for those who believe in the Hollow Earth Society, that way, or members of the Hollow Earth Society, supporters of, there's not this gravitational pull inside, and so basically people can live inside there because they want to go straight, and so they're basically sort of plastered up against the wall, kind of like the oaken bucket problem. However, the Hollow Earth does not explain the seismic data that we have. Questions? Realize that if point P had been on the outside, say this distance, so this distance here is little r, the only thing that would change are the limits of integration. If it were outside, then the closest it is little r minus big R, and the farthest away would be big R plus little r. So that's the only switch if we dealt with outside. If we went through all that math, what we would end up with, it's more complex, so a plus for doing the inside one. If we did outside, what you'd end up with is G times the total mass of the sphere times the little mass over R squared. In essence, it's the formula that we started with, I guess, negative I hat for direction. Now, another reason for doing this, even though I don't do much with the strange shapes and ask you to go through the calculus of it, although there are certain temptations at times, but there's too many other things I'm trying to test you on, and Lawson would not approve, is when you're dealing with electric fields and charges, or what is the electric force on a charge inside something with uniform charge density, the same thing applies, and I exploit that more. That is something that we do exploit more in the second semester course. So at least this is an introduction to it. So the second semester course is, you're seeing the derivation, somewhere in the back of your mind you're going, wait, this looks really familiar. And you can jump to the chase of, oh, it's recorded. Just change the M's for Q's and you're good to go. That's where I put it. Okay. So let's talk about tests. Quizzes, stuff like that. So you got the quiz on Thursday. It's always that balance of how much new material do we do before. I don't want to do that right after fall break. So the 20th, the quiz on 6 and 7 combined. Now, test corrections are also due that day, and some people have an objection to too many things due on the same day. Test corrections, for those who have it, that should still be a target, but if they're not ready on that day, just let me know when I'm gonna see them. I just want it off your plate. And let's make the 27th test 1B.
And that's chapters 5 through 7?
Yes.
That'll be for what?
Test chapters 5 through 7, test 1B on October 27th.
Test.
What exactly would like the questions be for a quiz on chapter 7?
Oh,
Like, what would you be solving for, like,
the
the mass of?
they're from the textbook.
So just studying the homework.
Yeah, so but your question is about on,
I mean-
with that quiz right there?
Cause like before we did like that up there, we pretty much just found the one formula, is that just what we would use?
Yeah, the gravitation all centers around that one formula.
Okay,
I feel like I'm not understanding your question.
no, I think that,
Okay.
And David, 1B will be in which chapters?
Chapters 5 through 7.
And can you repeat now about Master Series 6 and the lab, which day?
All right,
I
so
gotta
we
write
got-
up the whole thing.
Tuesday, Thursday, the 6th, that's today, master set 5 due. Thursday, master set 6, and the quiz, the homework quiz on chapter 5. The 13th is fall break, not spring break as I keep wanting to say. The 15th, that was the 8th, 15th, we got the centripetal motion lab due, and presumably another lab. I still need to post the lab for this week. The 20th, test corrections due, and the homework quiz on 6 and 7. And 22nd, probably some lab due. Ooh, actually. So the 15th, we'll do class and not a lab. So whatever lab we're gonna do on Thursday, that'll be due on the 22nd. So that lab is due then. And then, so that way you don't have 2 labs due on the same day. And then the 27th, test 1B, chapters 5 through 7. I think that captures the beauty of it. If you would like the test sooner, we can do that. And there's less new material covered before then.
Homework, what?
Homework quiz, that's the HWQ, homework quiz, chapter 6 and 7. And then master set 7 is not going to be, I'm not going to assign master set 7 to be handed in. However, if you would like, you can do master 7, I'd be glad to look at it, or I can just post the solutions also.
Homework quiz is just a quiz.
Yeah, that's, I take problems from the, assigned problems from the book, take 2 of them from the chapter and change the numbers.
Okay. What is this? This is the same. No.
All right, so while you're figuring that out, let's take a break, stretch legs, and then we will come back and talk about new stuff. Again, using the technical term. So that's what you missed up there. Oh, I guess whoever's watching it got saved from the grueling, what 3 things do they have in common? Now, conservative work caused by conservative forces, and so obviously I think the question is, what's a conservative force? To date, we've dealt with one. So the easiest way is the checklist. I'm going to give you the formal definition, or slightly formal. If I have an object at some point, and it experiences the force and does a round trip and gets back to where it started, if the kinetic energy has not changed, that's a conservative force. So if conservative force applied through round trip or through circuit, I guess closed circuit, if delta K will be 0. Well, which force do we have we worked with that if you apply it, an object will get back to where it started from and be going the exact same speed it started with?
You repeat that?
All right, which force have we dealt with which we have dealt, that if I expose the object to that force, it will do a complete round trip, end up back where it started, going the exact same speed that it started. It's looking for, centripetal is always some combination of one of the other forces, so not centripetal.
Planet?
Did you say planet?
Yeah.
What? Okay, I think you just said it.
Earth?
Oh, no.
No?
What force is involved?
Gravity?
Yeah.
Gravitation.
Gravitational force. Gravitational force is the one force we've dealt with that's conservative. So the other way, instead of going through this, and I can write it out more formally in calculus, or I could just say, here's a checklist. Gravitational. Conservative forces. That's the only one we've dealt with up till now. We will add to that at some point, as near the end of the course, the ideal elastic or spring. That will be a conservative force also.
So conservative force and conservative work aren't exactly the same thing.
Conservative forces do conservative work. See if I can do that less muffled. Conservative forces do conservative work. Non-conservative forces do non-conservative work. Now, why do you suppose they call them conservative and non-conservative? What's being conserved? So conservative work conserves energy. It's not conserving kinetic energy, it's conserving energy, which means that I gotta have two types, because if I have conservative work working on an object, for instance, I take this marker and I let go, the kinetic energy definitely increases as it falls. So if my kinetic energy is increasing, if energy is conserved, that means something else has to, so if kinetic energy increases, something else has to be decreasing to offset that.
Potential.
And so we get into mechanical energy. There's kinetic and potential. And I'm going to write energy after this one because I need to get to the habit. There's gravitational potential energy, but there's also something else called gravitational potential. We're not going to do much with gravitational potential. In the second semester course, we'll deal with electric potential energy and electric potential. Those are two different things. They're related to each other, but they are different. Well, if you think about it, this is all being developed under classical physics. I think conservation of energy first was proposed in the 1800s. And which is somewhat surprising considering Newton came out with his stuff in the late 1600s, so we've got over a 100-year period here. But in classical physics, all objects have mass. They have mass. They have some speed. Could be zero, that is a speed. And they have a position. The speed relates to kinetic energy. The position relates to the potential energy. And now I'll introduce the symbol I use for potential energy, the capital U. And mass relates to rest energy. I bring up rest energy for completeness. It was not included over here because when you talk